thing, use kind of the same methods, so it's nice to present today here. And of course, if you have any questions, you can also raise questions immediately. So if you feel like, okay, I have a question, just raise your hands, no problem at all. And today I'm going to be talking mainly about anxiety. Complicated to describe. Are we now fearful or are we anxious? The interesting part is if we define it more as the unpredictability of threat or predictability of threat. So anxiety is more this kind of state. You are in a dark wood. You cannot really tell, is there something threatening, animals, whatnot. So you are in this state of negative apprehension. You expect maybe something, but you don't know what and when. So this is what we would call anxiety. And the idea is also that our attention in this state is very much wide. You are alert because you don't know, is there an animal hiding behind a tree? So this is a very broadened attentional focus. In your face, then you clearly identify the threat. Your attention narrows down to the threatening source. So you have very selective attention, and this is what we assume to be fear. So the difference is predictable threat, because here it's very clear what the threat is. We were interested, can we disentangle these two kind of negative states by using different kind of experimental paradigms, but also electrocortical measures. Of course, we were not the first who thought about this. So this is a very influential paradigm from the group of Christian Guyon, where they wanted to assess these two states in the same paradigm in humans. So they call this the NPU threat paradigm, and NPU stands for no shock, predictable and unpredictable condition. In the neutral or no shock condition, that's the control condition, no threat at all. You hear some noises sometimes to measure startle responses. You see some cues, but there's no electric shock at all, so a control condition. In the predictable condition, every time a cue shows up, or almost every time, a shock is happening. So it's very predictable. You know when the cue occurs, then there will be a shock. That's why we call it the predictable condition. And we have the unpredictable condition. You also see a lot of different cues, and you know there will be a shock at any time, but the shock can really happen at any time. So the cues do not predict anything. Hence, you are in this unpredictable condition. And they used this paradigm a lot of times, and mostly they measured startle response, so the blink response to loud noises, which we know is a readout of the amygdala activity. And what they typically find is, especially in the predictable condition, when there is a cue present, then there's the largest startle reflex, the largest fear reaction, so to speak. Because there, it really matters to have the prediction of the cue available. Whereas in the unpredictable condition, the cue doesn't have any information for you, so that's why the startle response is the same. Whether there's a cue or not, you have the same amount of startle. So that's why they thought, okay, here we really model this fear state, concrete threat, enhanced startle. Here we model this anxiety state, because whenever a startle occurs, you are in this anxious mood, so we have enhanced startle responses. Now we wanted to adjust this paradigm to measure electrocortical activity via the EEG, and we used a method which is called steady-state visual evoked potentials. And this is basically done by flickering a stimulus at a frequency. So the stimulus is presented at a certain frequency. You do several trials. You record the EEG from the skull. And when you average about 10 trials, then you get a really nice, clear, so-called steady-state response, which is exactly at the same frequency you are flickering the stimuli with. So the visual brain, but that's true for all sensor modalities, basically resonates at the very frequency you are stimulated with. We can do time frequency analysis on this frequency to identify how present is this frequency at any given time in the brain. And we know from a lot of studies, also from here, but other studies, the larger this amplitude of the signal, the more attention is the visual brain paying, or the more the visual brain is busy with this stimulus, especially when it's a motivationally relevant stimulus. The good thing about this signal is that it's very strong and it's very clearly located, so you will always find a strong response in the time frequency spectrum. Here you see the power of a fast Fourier transform, and when you look at the topographies or do a source localization, you can also see it's very narrow, coming from mainly primary visual cortex areas. So that's good to know, because then we know the signal is really originating from visual cortex. Now, one feature of this paradigm is that you can now add several stimuli to the visual field and flicker them at different frequencies. So at the same time, showing one stimulus here at 14 and the other at 17.5 Hertz. That means when you record the EEG, now of course you have a messier signal, because you have 14 and 17.5 Hertz overlaid in the very same signal. But since you know which phase, for example, in this paradigm is flickered at which frequency, you can analyze exactly this frequency in time frequency analysis. So you can basically disentangle the two stimuli and make claims about, oh, this is a little delayed. Sorry. Make claims about which stimulus kind of wins the race for attentional resources in the visual cortex when they are competing at the same time. And this is the technique we basically use to adapt for this NPU paradigm to see how these different conditions lead to different attentional processes. So we did this paradigm. So we have our three conditions. Now we instructed the participants, you will know you are in the N condition when these four quadrats will be flickering in the periphery of the visual screen. You will know that you are in the predictable when it's triangles, and you will know when it's unpredictable when it's the circles. So now you have to imagine this is going on for 30 seconds, constantly flickering at 15 Hertz. And then within these 30-second streams, we insert central cues, flickering at a different frequency, only for 3 seconds, but very important, predicting the shock in this condition, because we are in the predictable condition. In the other conditions, they don't predict anything, like in the original paradigm. So with the idea, we can now analyze activity to the contexts, and at the same time, the activity elicited by the cues to disentangle what happens in the brain, depending on what information is available. So this is a kind of simulation how it looked like. It's of course faster, so it's a lot of flickering going on the screen. You also have to make sure that you have participants who don't have epilepsy. Oh, this is all in. This is basically just to show you that, again, we can disentangle the two frequencies, and therefore we can also make claims about which stimulus was processed in the visual brain at what time. So what I show you here now is the onset of the we name it contexts. So no cue is yet present in the middle. It's just that you know, okay, now I have the neutral, predictable or unpredictable context, and we average the respective frequency spectra here for the first second. And what we see is that the unpredictable context elicits the largest activity, so the most attention, the most stimulus processing is going on, which is kind of conform with the hypothesis. Unpredictable context immediately triggers this widening of attention, because now I know sometime during the next trial there will be a shock. When we now look at the activity elicited by the cue, so now we are basically looking at cue onset, and here we look at the whole cue processing of the 3 seconds. Then we find a different thing, namely that the predictable cue gets the most attention, has the largest cortical activity. Again, also in line with the idea, once there is the predictable threat, attention focuses on the actual threat. So this would be nicely in line with the predictions from different theories. Now the question was, what happens at the same time with the surrounding context? Because they are still going on, right? So you could assume if there's real competition, the processing of these contexts in this condition should go down, because now the attention is selectively focusing in the middle, so there would be less resources available. So let's look what happens. Surprisingly, not competition. So this is now again the activity for the context, the surroundings, at the same time when the cue was presented, where we also had this enhanced processing of the cue. But what you see is indeed also the contexts are enhanced. So it's actually an addition, not a competition, which was something we did not expect, but which we maybe can explain that with this very abstract stimuli, only the combination makes the most prediction, so to speak. So it's kind of a gestalt binding. You bind both the central cue and the outer cues to one big stimulus, and therefore you maybe also process these outer stimuli enhanced.
Can I ask you a question?
Sure.
Did you look at the commodulation frequencies? So, for example, what was it, like 15 and 20, so at 35? So, because this could be like a measure for this binding.
Yes, I think we did, but we did not really see anything going on there. But it's quite some time ago, so I'm not clearly, I don't remember exactly if we really looked at it, but clearly we had the idea of looking at it. I think we didn't find anything in that. Any more questions so far? In a later experiment, we were a little bit more like, okay, these are very abstract objects, so let's bring this a little bit to the real world. So we used as context screenshots from actual virtual reality rooms. So you have a room with different chairs and stuff like office, which would predict the NPU condition. And as cues, we just put someone in the middle of the screen, a face which looks differently, so that you would know, okay, with this person, this would be the cue for the predictable shock, or in this case, noise. So basically the same paradigm, different stimuli. And here we show the overall activity elicited by the background picture, so the context. And here we again find, but delayed, enhanced activity, especially for the unpredictable contexts. We also find enhanced activity for the predictable cue in the middle, but this time it's not that clear. Oh, sorry. This time, this effect is not so strong as compared in the first paradigm. So here you only have this difference between the P and N condition, but this difference is not significant. And we also did not find here this enhancement for the context during, which is probably also, this is a much more complicated visual scene, so maybe there the binding does not really work. But we were kind of, satisfied that it mainly replicates the findings from the squares and objects, so that it is not only due to this very simple paradigm. Here we also recorded heart rate and skin conductance, but this is now the heart rate response to the different conditions. So this is the onset, again, of the background picture. So no Q in the middle, but you know, okay, I'm in the NPU condition. And we see here in both threatening conditions deceleration in heart rate, which is not different between the two threatening conditions. So a general, some call it fear bradycardia, because they know either way, I'm now in one of the two threatening conditions. When we look at the heart rate in response to the cues in these conditions, we see, interestingly, an acceleration, but only in the predictable. So when the predictable cue is on and you know, okay, in 3 seconds there will be this aversive noise, then your heart rate immediately is activated, which is kind of, interesting, because we could also expect a fear bradycardia at that point, but sometimes this could also be the activation already for any kind of option of avoidance, which in this case was not available.
I have a question.
Yeah.
Did you also see a relationship between something like, because people show a defense response to the predictable cue?
Yeah.
So with heart rate acceleration, so they activate their sympathetic system or lower their parasympathetic input. So what's the relation? Like people who showed more defense response to the central cue, that were those that showed more deceleration, fear bradycardia to the context, because they used more attention, something like this.
That's a good question, but I don't think, we didn't analyze that. That's a good idea to look at, but we did not do that.
Okay.
For us, this was more like this proof of general heart rate deceleration as a response to threat. Good point. Now, in the next studies, which are from my then PhD student Yannick Stegmann, he wanted to combine these kind of threats a little bit more in a controlled way, because in this original paradigm, of course, the acute and potential threat are very separate, but often, or there's also theories that this is not completely discernible. Sometimes we are in potential threat conditions, and then of course the threat appears. So how does this add up? Does it just add up, or does it interact? So he wanted to see, indeed, what happens. Does it interact, or is it an additive model? So what he did is basically first a cue conditioning. So there's a conditioning where these Gabor patches were paired with shocks, and these were not paired with shocks. So participants learned one of these patches is the threatening cue. And then in a test phase, these cues were now presented in aversive or in neutral contexts. So now you would mimic a situation, the aversive context is there, which you naturally would be more anxious, and then all of a sudden a cue appears where the actual threat is there. So we combine the potential with the acute threat and see what happens, again, for the processing of the acute, but also for the context cues. This is now heart rate data, the context onset, so no cue in the middle present, a clear heart rate deceleration for the threatening context. When we look at the Q onset, we see mainly main effects, namely all threat cues. These are the blue, the dark ones, show a heart rate deceleration, but also all more threatening contexts, which are the triangles, show also heart rate deceleration. So basically, no interaction, but an additive model of more threat leads to more heart rate deceleration. This is also true for the threat ratings. This is also true for the steady state evoked potentials to the Qs. So in this paradigm, only the Qs were tagged with steady state. And this is also not completely true for the skin conductance. Here we only had a Q main effect. So between the two Qs, there was a differentiation between threat and non-threat. So this looks more like additive models than interactive models of threat. He also tested this by Bayesian modeling, so where you can basically test how good is your data looking as an exclusive model where no effect will be present. Additive model where just context adds something to the Q activity, or this interactive model where really these two factors interact. And this is now done for the steady state responses. So this is always comparing to a null model, the null hypothesis, where you see there is much more evidence for an additive but also an interactive model. However, if you compare these two, there's no difference. So we cannot say, even though it looks stronger here, a direct comparison does not lead to the conclusion that interactive is better than additive. So we still don't really know. There's evidence for both, but clearly there is some evidence for enhancement of Q processing via the context.
So if you're in an anxiety-inducing environment, and then a real fear cue appears, a real danger, then your response is potentiated.
Yes, but not that much more compared to the safety cue, because that would be much more interactive model. And he tested the same also one more time with both. So the contexts were conditioned and the cues were first conditioned separately, so that you had a clear for both learning and not inherent threat, to see if basically this replicates the previous findings. So then in the end you would show the conditioned context as threat and neutral context, and then the conditioned cues and neutral cues. And again, in this case, only look at psychophysiological measures. And here the interesting thing is the contexts did not really work or have an effect on heart rate. We think that it is takes much longer to learn.
What's the difference between the threat and neutral context? The image is different, or what?
No. So here the idea is, sorry, I was too fast. The idea is that both images are just boring street images, nothing inherently threatening. But we do a conditioning procedure. So this context, this picture, this street will be predicting aversive noise at some point. And then afterwards, you do the same actually with the cues. So now both have gained threat relevance, but separately. And then in the test phase, you combine both of them. Whereas in the first experiment, the threat value of the picture was already there because it was a really mutilation picture or something. So the idea was more compare it now with compared learned threat. And then you already see apparently this learning of threat with not many trials, that does not lead to these strong heart rate decelerations. Therefore, we also don't find any effects of the context in the Q onset heart rate. You do find a main effect of context for threat rating, so a more cognitive approach. People could identify, okay, this is a picture which was paired with a shock, therefore it must be more threatening. And in the skin conductance, again, there was also only a Q effect. So the conclusion would be to have acquired context and acquired Q combined. There, the strength of learning of the context is very important, and we think this was just too few trials to establish a strong threat context. Okay, now I switch a little. Now we were in the predictable, unpredictable threat. We also did some studies on fear generalization, which is of course also related to predictability, because we think if you can hardly predict if a dog is will be biting you because he resembles a dog which actually bit you a couple of years ago, then you have this fear generalization process going on. And then you have this more safe than sorry strategy. Well, if it looks kind of the same, then probably it's a threatening animal. And that is, of course, all based to the famous little Albert experiments, where after being conditioned to the white rat, he basically feared everything which was white and furry in the end. So that was like the first demonstration of fear generalization. To investigate that again experimentally in the lab, a classical experiment is you do fear conditioning. So you condition one stimulus to be safe and one stimulus to always predict threat. And then in a generalization test, you basically test stimuli on a gradient resembling more the threat or the safe stimulus. And by this, you would test if people show a strong reaction even here, they would be overgeneralization. You know what I mean. We also, to have this more socially relevant, you can also do this, of course, with faces and morphing. So you would condition to one face with threat, for example, and to one with no threat. And then in the generalization, you actually present morphs between the two identities to again see, do people also show fear or defensive responses to these stimuli. There's a lot of studies out there which claim that, especially for anxiety patients, a linear function or a more linear function of this gradient is resembling overgeneralization. So this would be patients, and this is healthy controls. And here you see much more quadratic function than a linear function. So what we always assume is a little bit quadratic trend in this function resembles a more natural, normal generalization. Whereas when this is getting more linear, then you have probably overgeneralization. Just to keep in mind when you will see some of these later. So one of the first studies we did together with Yannick was presenting faces, condition one face with, in this case, a US which was an angry, fearful face and allowed noise, and the other one is safe. And then you present all these faces in between, and of course the original faces again, and test how the brain reacts by doing again steady state flickering of the faces. This is just showing you that the conditioning worked. So in all variables, the steady state, the US expectancy ratings, arousal and unpleasantness rating, the CS plus in the end or an average is rated as more negative, elicits more steady state response. So just to be sure that conditioning worked. Now, how does it look like for the generalization test. Well, first, if you look at arousal, expectancy, and valence, you basically see and also then tested quadratic trends for generalization. And these were, of course, healthy students, so that is kind of what we expected. Interestingly, we don't see this in the steady state. Here we found this drop in signal actually for the one closest to the threat stimulus. Now, we were even more puzzled when we looked at social anxiety within the sample, because here we found a strong interaction, meaning that indeed the people who were high socially anxious had this largest drop in signal. At that time, we didn't really know what does that mean until we looked a little bit more in the basic neuroscience literature, and there is this phenomenon of lateral inhibition. So in the really primary visual cortex, a stimulus which is very similar to another stimulus gets suppressed in processing. And interestingly, apparently, for anxious persons in the visual brain, that happened here. So they do not do a generalization at all, but they make this strong drop in signal. So we, at that time, could not really explain what that means. Probably that generalization is not taking place in the primary visual cortex, but in higher order cortex. Or sometimes there's MRI studies where it's shown that it's even more related to insular activity. Interesting, nevertheless. Oh yeah, this is just to show you that if you model these different functions, then there was clear evidence for this inhibition model, where this huge drop appears between the two stimuli.
I mean, it makes sense somehow if you're highly anxious,
Yeah.
social anxious, and you have the phase that is paired with the shock. It's very adaptive to really identify the person who is like, who is threatening you, and in the visual cortex.
Yes,
of course, yeah, and maybe on more physiological measures that indicate activation of the body.
Yeah,
maybe there's more the generalization, so just in case.
Exactly.
Yeah.
So that is also what we think, that it's mainly it's a different output system, or maybe much more input system at that time. So yeah, clear generalization is probably taking place in other systems.
Sorry, maybe I didn't get well, but it's like the anxious people don't get the same results in the gradient than the control people. Like maybe the control people shows the gradient, like the response is like more linear and anxious, like to cluster. Or
Yes, when you then plot this a little bit dependent on social anxiety, so this is one standard deviation above and min, then you see that it's only the high social anxious here to have this strong drop, but in the middle you still see that, and the low anxious, but actually they don't do anything. So they don't even care between the different stimuli. So it seems that the activity that we are measuring from most likely primary visual cortex is just not that much involved in generalization. That is our conclusion so far. We then followed this up a little bit with a lot of experiments where we were interested, does this generalization appear when we manipulate, for example, predictability of threats? So here we did in a between group design different predictabilities of threats. So in this case, 80% of the stimuli would be followed by threat, or 60 or 40. So we hypothesized that maybe when there's least unpredictability, then there's more generalization in the visual cortex. But I make the story short. So this is again the acquisition, where only in the expectancy ratings you see a little bit of effect of high unpredictability, middle unpredictability, and low unpredictability. But that is basically just showing that participants learned quite good what the predictability is. So they are very close to the actual predictabilities. And when we look at the generalization, there were no effects. Interestingly, also here we did not find any kind of this inhibition thing anymore. So it seems really to be the case that it's the trait anxiety which shows this inhibition, but not any manipulation of unpredictability. We found some evidence that trait anxiety, in this case intolerance of uncertainty, is related to generalization, but not in the visual system, but again in subjective ratings, meaning that the high anxious are the ones who have again a more linear function compared to the ones who are anxious. So this is a little bit replicating other studies in terms of the ratings. We also induced the safe and threat context again, as we did in these previous experiments, and we're looking for, does the threat context induced by these outside arrays again change generalization, but it did not. I go a little bit faster because I'm thinking we're running a little bit out of time, and there's not that much results in this part. So the threat context has only an effect again in the conditioning, and this is basically also replicating what we saw earlier in the Stegman papers. Again, more pointing at a additive or interactive model that threat context adds up to threat cues. So this is shown here. In threat context, the differentiation between threat Q and safe Q is larger. But we were, of course, mainly interested in what happens during generalization. And again, there's almost nothing happening except for main effects. And in the US expectancy ratings, this seems to be the measure where you see, if at all, an interaction. But in all the other measures, it's mainly main effect. So of course, there's a generalization gradient, and there's a main effect that all the reactions are lifted up when you are in a threat context at the same time. Then she did the same with what we call threat relevance. So far, the phases we used to condition were all neutral. But then you can think of, yeah, but often we, especially also in anxiety, we encounter phases who look already inherently threatening. So this is basically doing the generalization test with threatening phases. So here we have a threat phase, and then it goes to another threat phase. Or we do the same with neutral, as we do all the time, to see if that inherent threat adds up to the story. But again, this is mainly main effect of stimulus in the acquisition and a little bit of a main effect of fear relevance. So, okay, fear relevant stimuli get processed a little bit more, but there's no interaction with the learning. And therefore, there's also not much going on in the generalization. Again, mainly main effects, threat relevance adds up to the general. So we think this is more like these series of experiments show that this generalization is quite a robust phenomenon, which is not that much influenced by external factors, at least how we manipulated factors. And it's, of course, a very adaptive mechanism that, and these are all healthy students, by the way. So, of course, fear generalization in general is adaptive. It's only maladaptive when it's overgeneralizes, and apparently that didn't do with the other manipulations. Okay, I go a little faster because otherwise I cannot finish.
A small question.
Sure.
In the predictability experiment, you did groups of subjects, no?
Yeah.
Each group had a 1% of probability. Is it possible experimentally to do a design, maybe it's impossible, with the same person and GS1, GS2, GS3, GS4 having different probabilities of being associated with a threat with the
Sure.
thank you. It is impossible to do it with one subject, is it?
I think then you confuse the subject totally, and I don't see that you then can still disentangle the generalization, because the generalization idea is, of course, that you generalize because of you learn one stimulus to be threatening, and all the others are just similar. So if you start reinforcing the other ones as well, I think you just add a lot of confusion to the learning system.
I go.
Yeah, in the last part, I wanted to give you a little bit update on what we are currently also doing in terms of bringing lab studies together with real life studies, so to speak. So what we started to do is we run our lab study, in this case, this attentional bias, so two phases, record the EEG, record a lot of physiological measures, but then the participants do ecological momentary assessment at home. So that means on their phone, they get prompts every day 3 times to fill in a lot of questions about how they feel right now at home, how positive, negative, social anxiety, worry, and also how experiments should avoid it. So if they avoid any threatening situations at home, with the idea that hopefully if our work in the lab is meaningful, this can predict real life behavior, or at least has something to do with real life behavior. So this is a large study going on, so I can only give you some preliminary data. We have now 198 participants through the whole procedure, and this is all due to this PhD student, Yao Ling. Now the idea was to look at the measures in the lab, all the variables that we have, run latent profile analysis, and see if these profiles that we find differ on the behavior at home, but also on the trait questionnaires of anxiety and depression. So this is the first result of a latent profile analysis. So we put these 15 indicator variables in a latent profile analysis, and then you get probabilities for the most likely possible profiles. And then you always have to make a decision for which solution you go. And the most likely was then this one, a 3-profile solution where you have 114, 59, and 25 people in the profile. Now, to make sense of the profile, you first look on the indicator variables. So this is now the 3 different profiles. And here we plot the indicator variables. So we can see a little bit how these profiles differ. And then we see that profile 1, the most people are high in these measures. So that's the blue lines here. And these are all the subjective ratings of faces. So it's arousal ratings and valence ratings. That's why we call them high subjective affectivity. Then we have profile 2, which we call emotional numbing, because there are persons who basically don't do anything and show very reduced arousal ratings in the task. So they have no real reactivity to the stimuli. Or we can also not exclude that they just don't do the task properly, so I have to say. And then we have the other profile, which is basically high psychophysiological arousal. So people who mainly react with the skin conductance but also with the heart rate to the stimuli. So now we can describe a little bit, these are the 3 profiles, and now we compare these profiles on the other variables, which is done here for the questionnaire data. So these are all the questionnaire data. You see not big effects, but you see that especially for the questionnaire data, the skin conductance, physiological arousal people show the largest values in generalized anxiety disorder questionnaire and the anxiety subscale of the DAS, which measures anxiety depression, which is kind of interesting. So the physiological activated people in our lab score higher on these measures, trait anxiety measures basically. But when you look at the daily life measures, so now we're looking at the ecological momentary assessment during life, it's the people who have these high effective arousal rating profile who score higher in daily social anxiety, worry, and avoidance behavior. Again, these are all borderline significant effects, but I think still interesting to see that at least there's some indication, and again, these are all students, that you can find some different profiles and that they may differ on the psychopathology measures. But then I came to Gainesville, Florida, and had all these data with me. This was just in February, and Alejandro was there, and Andreas is there, and they were busy with like autoencoders, so machine learning to reduce a lot of data, but also make predictions out of these latent dimensions. So we just put these data that we had in what is called a supervised autoencoder, because what we want to do is we reduce through the encoder the data to 4 latent dimensions, but at the same time we also want to predict the questionnaire data with this. So what you basically do is you want to minimize a loss function, which is basically based on the reconstruction, but also on the prediction at the same time. When you do this, now we put in also all the daily life measurement as input variables. So this is a different approach to the latent profile. So now we have 45 predictors, do the autoencoder and want to reduce this to the 4 latent dimensions. And with these 4 latent dimensions, we want to predict the 11 psychopathology questionnaires we have on these people. So when you run this, you get 4 latent dimensions with all the variables shown here. I will later come back to what it exactly means, but you see, for example, a big difference. These are all the daily measurements. So the ecological momentary assessment has quite a huge difference and power in this model. But you also see steady state evoked potential here, which are really the opposite sometimes. Now the question was, how good do these 4 latent dimensions predict indeed our questionnaires? And I don't have everything here yet, and it's also still work in progress, but we were quite surprised by quite high explained variance, and this is social anxiety. Then you don't believe what you see, but we have checked it a couple of times. So the 4 latent dimensions predict the social anxiety questionnaire, yeah, unbelievably good. We still have to check, leave one out, and all these measures to really see how good that is. But I think it's a quite interesting first set of data where you can see how to use that probably to make better predictions. And I think the main advantage compared to the latent profile analysis is that this takes nonlinearity much better into account. You can then also plot just the factor weights to see which of these 4 latent dimensions explain most of this questionnaire, and then you see, For example, here the profiles or latent factors 2 and 3 have this strong positive, and the 4 the strong negative, and again very strong. So these are a correlation. Or for the alphas, where you see it's really a complete antagonist pattern, that 2 factors are very predictive and 2 anti-predictive, but also predictive. And if you look at this, so the 2 dimensions who were very predictive are latent dimension 2 and 3. 2 is the one here with this middle daily life negative emotions, but 3 is this very high negative emotions in daily life. But the interesting thing is this goes ahead with this pattern here, which is an attentional bias in the steady state, so an attentional bias for threat. But this one goes with an attentional bias away from threat. So you now find 2 kind of participants who have daily life worries and all that stuff, but show in the EEG data opposite mechanisms. And this is what we always kind of thought of attentional bias, that there are 2 types of people. There are people who have this early initial vigilance and therefore are anxious, but there are also these people who immediately avoid. And I think, but really all preliminary, with all cautious, but this looks like very interesting that we now have 2 profiles which have here the opposite, but here a little bit the same. And again, this is combining all the factors.
So you have a name for the different, for latent dimensions, or you don't have like a name to give to all the dimensions? I don't know if I explained that. Like, you have 45 predictors, and with those 45 predictors, you get 4 latent dimensions.
Yes.
Do you have a name for these dimensions or not?
Not yet, because with 45 it gets a little bit more complicated to really interpret, and we still also need to figure out how do we test if this really is a meaningful pattern compared to the opposite. What is the statistical measure to say this is really a meaningful difference? I mean, for this one and this one, it's almost obvious that this is a different pattern, but here it's much more subtle, and we have to figure out how we can express this in statistics. But I think it's an interesting start, and a lot of things can be hopefully detected with that.
And do you think that you can use this, or is it maybe not interesting also, this for screening your subjects, to screen your subjects for later experiments, or to go back to your data and reanalyze? Do you think it doesn't interest you, or maybe?
Well, the original idea of a lot of this work is, of course, that you need more personalized approaches to clinical psychology. And it would be ideal if you could do that and identify single persons, but this is also far from that you really can tell one person belongs exactly to this dimension. We didn't have now kind of reconstructed which person sits actually in which dimension. So this is all now in latent dimensions, not in subjects, really.
I understand.
I wanted to ask you, here, for me, it was the difference between this one and the other Bartlett. I think it was the guy, the previous slide. Yeah.
Sorry.
So,
Which one?
Yeah, this one and the next one. So the first dimension here is not absolutely related, and the other one are quite significant.
Yeah, but it's a different question. Yeah.
So it's like for 2 different questions.
Yes.
This dimension is like this dimension is very sensitive for which dimension, for which questionnaire are you talking?
Yes.
Okay.
But of course, it's always the combination of the 4. But you can, I think, based on these factor weights, you could say for the general anxiety disorder questionnaire, this dimension apparently doesn't play a role. They don't remember now by heart where they were in the graph, but I think you could also say for this social anxiety, apparently all 4 play an important role.
Okay, so this could be like a kind of tool to identify well, because sometimes social anxiety has been a bit confused with general anxiety. So maybe this could be like a kind of tool to discriminate very well these two populations, or
Well,
very
that would be very early, and I would not make these claims yet. But of course, that could be the idea. Yeah. And I didn't show in our audit, we have these like 10 questionnaires, and really it differs quite a bit between questionnaires, but you also see that these two, since we all have mainly questionnaires about anxiety and depression, that these two dimensions apparently are the most positive correlated predicting anxiety and depression with traits. So in an ideal study, you would include much more different spectra also of disorders, for example. And of course, also the whole ecological momentary assessment was basically designed for measuring anxiety and depression. So it's also not that surprising that this very well predicts then anxiety and depression questionnaires. But the combination of all the measures, I think, is the interesting. I think I skipped the last part because I'm hot. We also started a little bit like having more lab tests in one big sample. So also with the idea, you know, if you only measure field conditioning, you're also leaving out a lot of other processes. So what we did is you have a field conditioning paradigm, an attentional bias paradigm, and a decision-making paradigm with the same participants. So again, data from almost 200 persons, and then you see, again, do you find patterns in these three different paradigms across a lot of variables. We have not done this yet at all. This is more like showing you that there are indeed also correlations between the different paradigms. So this is an ERN paradigm. I'm not sure if people are familiar with that. It's basically how we measure EEG while people are making errors, and we know that people who are high on anxiety have a larger component in the EEG to these errors. And the other is then skin conductance condition, steady state extinction conditioning, and you see there are in 188, 182, 186 persons, there are these correlations. So we think some people really show in one paradigm this pattern and in the other this pattern. So we think there we can also use some of the machine learning or the profile analysis to see how this is related. But now I think we are all due to a break. So here's my short summary. I think what I wanted to show you is that we use a lot of measures, but mainly steady states also to disentangle attentional processes in anxiety and fear. That generalization of fear seems to be very strong and not that easily influenced by other factors. What we do now and think also is a way to go in search for real causes of psychopathology is more this multi-paradigm approach, and of course also using new methods in larger samples to find out how these measures are actually related or predicting psychopathology. Thanks for your attention.
Thank you very much, Matthias. I don't know if you have general questions or, well, whatever questions already, whatever. So maybe if you want to do some 2 or 3 more questions, but then I think we'll leave it. So if you want to have some questions, feel free to ask. Or if you're fine. So thank you very much.
Thank you.
It's very interesting. I think the last part is very interesting to see these latent dimensions, and tomorrow we'll talk about it. I will show some hardware stuff I did with autoencoder, inspired by your talk actually, when you were here last time. So I think there's a lot of going on the method side, how to how to characterize responses in general, psychopathology or physiological
Yeah.
responses, and bring them together to predict other variables. Yeah. So thank you again very much.
Yeah, thanks.
Tienes que ver.